Question number 9 on the worksheet tells us to solve this first order boundary value problem. This is a boundary value problem because you're not given an initial value of 0, but you're given a boundary value, something other than 0. And given any other value, any point on the graph, you should be able to solve for the constant of integration. So here we have a first order ODE, and this is not considered, or this is not separable because however I manipulate this, I cannot write the derivative as a function of y times a function of t. But I can, this is linear if I take the equation and divide by t. So let me divide each term by t so that I have dy dt plus 2 over t times y is equal to t squared. Okay, so I have my derivative term plus I have a function of t multiplied by y is equal to another function of t. This is linear form. I can find my integrating factor. In this case, my integrating factor is going to be a function of t, and it's going to be in the form of e raised to the integral of 2 over t. We're integrating with respect to t. That 2 can come out, and when I integrate 1 over t with respect to t, I get natural log of t. Now, whenever you see e and a natural log together, you want to suspect that you can cancel something, because those are inverses of each other. Here, you can bring that 2 up and make it an exponent on the t. You can rewrite this as e raised to the natural log of t squared, and then e and the natural log cancel to leave you with just t squared. T squared is the integrating factor, and you want to go back to your linear ODE and multiply every term by that integrating factor. Multiply through by t squared. When I multiply by t squared, it's going to give me t squared times dy dt plus, see here, one of the t's will cancel. It'll still leave me with another t. 2t times y equals t squared times t squared gives me t to the 4th. And now remember that when you introduce the integrating factor, you should be able to rewrite this left side of the equation as a single derivative. Derivative with respect to t, take that first factor, t squared, and then multiply by your dependent variable, y. And to double check, think of this as your u times v. The derivative of u times v is u prime v plus v prime u. U prime is 2t, so you get 2t times y. There's our 2t times y plus v prime u. The derivative of y with respect to t, dy dt, times t squared. And that verifies. Equals t to the 4th. And then your goal here is to get rid of this derivative. You can get rid of the derivative by integrating. And so we want to integrate with respect to t on both sides of the equation. And on the left side, this integral and that derivative will cancel each other out. let me bring this down here, to leave me with t squared y. And on the right side, when you integrate t to the fourth, you're going to increase the power, divide by the new power, t to the fifth over 5, plus the constant of integration. Now, here, because I can solve for y, I want to. You always want to solve for y if you can. Solve for y by multiplying by 1 over t squared. And that's going to give us y equals t to the third, because 2 t's will cancel, over 5 plus c over t squared. This is our general solution. And then, because this is a boundary value problem, we want to go back and we want to solve for c. We can use the fact that y of 1 is equal to 0. Y of 1 says that x or t is equal to 1. That's going to give me 1/5. 1 to the third is 1, plus c over 1, and from here I can just bring the 1/5 over to get c is equal to negative 1/5. So my particular solution is t to the third over 5 plus negative 1/5. Let me put that as negative 1 over 5 t squared. And this is the answer that you want for this problem.